Hello students, in this module we will take an example of fast frequency hopping MFSK system, and we will now apply our the knowledge of this active search acquisition mechanism for this kind of the systems, and we will try to find out how in a practical system we like this FFH MFSK. This search mechanism is applied, or search mechanism is accomplished. And remember with when we will discuss this typical system, we will carry forward all our previous knowledge of the basic understanding of serial search acquisition mechanism versus the parallel search acquisition mechanism, and we also understand what is the fast acquisition versus the slow acquisition. We learned about the FFH MFSK signal and the systems long back. So, we will quickly revisit how the system operates, and then we will enter into the search acquisition mechanism for this kind of system. So, let us start with a quick recap of this FFH MFSK signal. FFH stands for fast frequency hopping, and MFSK is the multitone frequency shift keying modulation going on. And remember, though the slide name is FFH MFSK systems and signals, we will also consider the slow frequency hopping MFSK systems. So, we will today discuss the active serial search acquisition process for the both, as it is active serial search mechanism. So, remember, we will have the correlator as well as integrate dump receivers. So, multiplier and integrate dump receiver, non-coherent and envelope detectors, all those components are expected to be present in the signal path rather than the match filter kind of architecture, which was we have seen, which is a passive device. And let us quickly first revisit the fundamentals of FFH MFSK system. We understand that what is MFSK. MFSK modulation actually changes the carrier frequency to one of the capital M tones. So, we have a bunch of capital M number of the tones, and if suppose my M is equal to 4. So, I will have F1 to F4 number of the tones or the frequencies to choose my transmitted data. So, for 00 transmit data, I may be choosing frequency 1, 01 I may be transmitting over frequency 2, 10 I may be transmitting over 3, and 11 I may be transmitting over 4. Okay. So, these are the capital M possible frequencies around the carrier frequency over which the MFSK modulation happens, and MFSK modulation can go on. And for fast frequency hopping, the capital M array frequency is the same over the hop duration. So, and remember that when it is a fast hop or a slow hop, in order to identify that, we did like this. We are compared to the duration of the symbol, if it is the symbol duration Ts, and if this is the hopping duration Th, then if we find that symbol duration is more compared to the hopping duration, such that within a symbol you are hopping over the multiple frequencies, we call it a fast frequency hopping. And is as if actually a same tone once sent on the frequency 1, and then you sent over the the one MFSK tone is sent over one hop frequency to, and then immediately changed to another hop frequency. If that is the situation, then we will call it is a fast frequency hopping. Instead of the case in the slow frequency hopping, the same symbol actually will maybe within the hop duration, over the hop duration, you are within a symbol duration, there is no hopping over the frequencies, and at least we will be assuming for this today's discussion that for one MFSK tone is getting transmitted over one hop duration for this slow frequency hopping. Okay. So, we will have one set of capital M number of the frequency set for the modulation, data modulation, and there is carrier hopping. For hopping, actually I have another set of the frequencies, say capital F, where the components of the capital F is F1 to say capital Fn, where over those frequencies they are the hopping frequencies over which the hopping is going on. So, one is actually because of the MFSK modulation, you are having a set of the frequencies which are getting used for modulating the data, and this modulated data are now hopping over the multiple frequencies. In case of FFH, the hopping speed is very fast, and in case of SFH, per modulated symbol, one dedicated hop frequency is there. So, that was a fundamental idea and fundamental understanding that we have recapped for understanding what was the MFSK signaling scheme and what is the meaning of this SFH MFSK or FFH MFSK. Remember, whenever you are thinking that there is a FFH MFSK, for each and every hop there are we will consider that for there are total capital N number of the hops, and the number of the hop per symbol duration, that is not varying, that is constant. So, this is the circuit for this active search acquisition methodology for FFH as well as SFH MFSK signal. Structure will little bit vary when the modulation, when the scheme changes from SFH to FFH. I have given here two different figures. Figure 1a is the combined figure of the acquisition mechanism, where actually the non-coherent demodulator architecture is separately given in figure 1b. So, 1b is basically zooming inside these blocks and showing the architecture what is there inside the block. And we understand the overall system acquisition is such that you are having the incoming signal, and the local PN generator is generating the codes and driving the frequency synthesizer to choose a typical hop frequency based on the controlled by the codes. And we understand that the code used for the hopping in the transmitter is well known in the receiver. So, the code that is getting generated exactly actually the same that is there in the transmitter, as well as they are perfectly synchronized for the time being. So, if they are perfectly synchronized, then your whole output, then you will be getting a perfect output, well synchronized actually down signal in the ZT. When the band pass filter, it will be simply passed by the filter activities, and the demodulator will be demodulating them exactly at the frequency IF, the intermediate frequency, plus the wherever the data modulation frequency is residing from FS1 to FSM. Scalar detector output will be detecting it, and then the output of all the detectors, outcome of all the detectors, here the maximum will be selected over for each and every th second, n into th second, and as we are having n number of the hops within a symbol duration. So, symbol duration will be consisting of how many number of the hops you are having over with the hopping time, and any the maximum value will be again sent by the threshold comparator to update the clock. So, that is the whole block. Remember, once you are getting a perfect synchronization situation there with which I started, then actually the output of these detectors, will output of the detectors as well as scalar envelopes and addition, detection and the adders, the output of all the adders will be exactly high. I mean, demodulator or detector output will be high for all the shifted modulation schemes and all the different kind of the hopping modulation schemes, and then it will be giving you the perfect one, and there will be actually no changes in the update, no update is required, and there will not be any threshold comparator output will give you perfect 0, and there will not be any changes required for the clock, which does not happen in the practice. So, though PN sequence generator and they are sitting in the receiver has some knowledge about what is that PN sequence used for the transmission, it has no clue at all actually about the phase information about that. And hence it is heavily expected that the incoming signal and the locally generated PN sequence will not be in sync, and there is a requirement of the active search acquisition mechanism. Here in this block diagram, all this NC demod stands for the non-coherent demodulation. That means, I wish to remind you that non-coherent demodulation means you do not have any information about the carrier phase, and carrier phase synchronization is not yet done in the receiver. In presence of the carrier phase ambiguity, you are trying to do the active search acquisition, and hence it is a demodulator and the square law detector output that with which we are relying on, and the selection of the maximum will be given, all will be given almost the same kind of the values if they are perfectly aligned, if the two codes are perfectly aligned, and hence there is no output at the output of the comparator. Before going into the explanation in detail, let us see little bit what is there inside the non-coherent demodulator architecture. Inside the non-coherent demodulator architecture, we are this demodulator is sitting inside the demodulator. There are the I path and the Q path, and the signal here is getting generated for the, it is generating both the in phase and the Q phase carriers, where the carriers will be in the intermediate frequency plus the modulated frequency shift. It is a shift over the modulated frequency that is expected to happen with respect to the center carrier frequency. And the I and Q signals, the carriers are getting multiplied with the incoming signal. That incoming signal here is from the output of the band pass filter. So, remember the signal bandwidth will be capital B only, and here is the integrator. The integrator is expected to integrate the whole signal over a duration of hopping time. So, it is 0 to TH for both the in phase and the out of phase carrier. Remember, this particular diagram is based on the slow frequency hopping. For the first frequency hopping, actually we have to we have to give a speed and we have to move fast, and the architecture will be also switching fast in between the carriers, and it will be little bit different. The architecture will be little bit, should be updated according to that. The integrator output, we understand that it needs to be sampled, and it should be fed into a square law detector. So, this device is a square law detector, and the switches, these are the cases where the in phase, I phase and Q phase sampling is going on. And remember, the sampler is sampling at the rate of 1 by the bandwidth. So, this bandwidth limitation came from the front end IF filter. The squared law portions, after the squared law output of the both in phase as well as the Q phase component of each and every non-coherent detector will be added in the adder, final adder circuit, and you will be expecting the output at the output of the adder. So, where are we now? We are here. So, inside this NC demodulated output, we have seen that we have taken the signal, we have done converted. So, that WIF plus actually thus WIST is there with us. Basically, this down conversion to the IF is IF, it may actually the choice of this IF may vary, and it completely dependent on you that how low you wish to have this IF for your typical circuit design. And finally, the output of this guy needs to feed inside the integrate and dump receiver, because that is the architecture of a non-coherent detector. And this integration is done over the hopping duration, and we consider it actually now if it is as it is a slow frequency hopping going on. So, for one symbol we will be getting over the duration of the TH only the one FSK modulated symbol coming inside. Sampler is sampling at the rate of the 1 by B, where B is the bandwidth that is controlled by the initial filter, I mean IF filter. Squaler detector is simply squaring them up the sampled signals, and finally, they should be added, and here your output is fed towards the maximum select each nth seconds. Remember, if I am having this kind of the architecture, so the frequency synthesizer initially whatever the output it is giving to the band pass filter, if it does not know actually what exactly where is your demodulation is going on, in which frequency the demodulation is going on. So, you will put the all parallel, that is why we have put so many number of the demodulators detectors here in the receiver path, and all the outputs, all this kind of the parallel inputs are checked all the time for each and every input, creating actually some output of it. So, out of all this, with whom the input will be perfectly synchronized, nobody knows, but once actually it is synchronized, then the output of that typical demodulator will be higher. It is added over the capital N number of the samples, and this added output and this output is added outputs for each and every branch or the path is entering into the select block diagram, and it chooses basically the maximum value wherever it is intuitive that whoever will be matching with the input signal, its detector output will be maximum compared to others. So, fundamentally this block's target is to choose the maximum output out of all the paths, and once that is detected, then he will be sending this information to the threshold comparator to compare the incoming signal, the difference between the incoming signal and locally generated one. The output of this, if it is some output is there, so then it will be included, it will be utilized to update the clock phase information inside the receiver section. Okay. So, this was the architecture, receiver architecture or the detector architecture at the in the receiver. Now, see some facts. If MFSK frequency is correlated over the capital N hops, it should be, because what I told that if it is a FFH signal, the same signal is transferred once in the hop number 1 and frequency number 1, and then within that how equation was completed, it was actually before that computation was done, it was actually driven to the other frequency to hop. So, the component of the same signal is there over the multiple hops. So, for the decision and the detection of that kind of the signal over the fast frequency hopping, we can have a good point that we can choose the value of the SNRs. We can calculate the value of the SNR over these multiple hops, and we can take the best out of it, or we can do some kind of the addition or weighted addition over all these different hops to get a choice or to have a better decision about the transmitted signal. And if more SNR is so overlapping is obvious over the n hops, the maximum is selected, and if more SNR is needed for this acquisition, the multiple MFSK symbols that can be combined over say ns number of the MFSK symbols that needs to be combined now in order to have more SNR required for the acquisition mechanism. And since we have assumed since beginning that the capital N is the frequency hops per MFSK tone, and now if it is the symbol duration is Ts. So, duration of the symbol should be always given by the capital N into Th. Because one symbol means you are having capital N number of the hops, and each hop is having the duration of Th. So, the total symbol duration for this capital N hop will be capital N into Th. And for fast frequency hopping, this each and every MFSK symbol frequency, this frequency will be same over the each hop. that we have also discussed at the beginning. And however, the phases, remember, though the frequency will be same over the multiple symbols, but phases can never be same, and hence actually due to the action of the hopping and dehopping synthesizer itself, we can never think of actually there will not be any effect on the phase, but there will be rather there will be a very big effect also, and the variation of the phase where the FFK signal, one FFK signal to the next will be really very high. And we have assumed in this situation that these phases are random in nature after each and every hop. And now we have also shown that figure number 1b, which is a detector details that the slow frequency hopping will be applied when the hop frequency Th is changed at the symbol period duration Ts. This is a time frequency diagram of the search mechanism or search acquisition mechanism. I will refer and come here once more while explaining this figure. Just to remember one thing and note one thing, that receiver and transmitter now they are not in sync, because of which actually the search process has started. Remember the difference between these two, I mean is denoted here, the frequency receiver frequency synthesizer's time gap with respect to the original transmit waveform is around epsa. That epsa is it needs to be minimized as minimum as possible, but it should not be actually on the opposite way, it cannot be exceeding the time intervals. Now, we will come back here. This timing assumption in the figure number 2 and the relationship of the frequency hops for FFH, MFSK and the MFSK symbols all are illustrated. It is assumed that when the receiver dehopping synthesizer is offset by say epsa seconds, as I have shown in the earlier slide, from the received hopping waveform, that the previous one that the previous one and the signal of the previous one and the signal of the next one will be actually quite different from the immediate one, and hence you can never actually, so that is why actually there will be typical detector output we can never be uniform over the time interval when before the epsa came, before the epsa duration and after the epsa duration also. The following hop frequencies and the sufficiently different from the current hop frequency, that it will previous hop frequency and the next hop frequency will be quite different from the current hop frequencies, that is detected and detected in the detectors of this figure number 1a. And with this assumption, the detectable portion of the signal will be of duration Th minus mod epsa. Okay. This is the portion that I have shown in the earlier graph. Come, let us go back. So, detector will only get the overlapping section of this gray area, So, because of the mismatch between the transmitter and the receiver frequency synthesizers, this is the only area or the time interval over which the detector can provide you some output. Okay. It may be necessary to accumulate non-coherently all the NS symbols to enhance the signal to noise ratio, definitely, because the structure itself is non-coherent architecture. So, the process and the mechanism will be of accumulating the signal to noise power have to be non-coherent in nature. The figure 2, now let us come to the row by row. Figure number 2 illustrates the time frequency algorithm, and the top row of this figure illustrates the data frequency, and let us go back. This is the first row, and this first row detects and first row talks about the transmitted MFSK sequence and their corresponding frequency, and we see that the rate of transmission of this frequency, rate of transmission of the signal is actually 1/4 than the hop sequence. That means, per symbol you will be hopping 4 times. So, transmitted hop sequence is part symbol wise 4. So, we are saying that the symbol frequency is 1/4 than the hop frequency. Okay. So, this is the row number 1 saying the modulated frequency rate, modulated frequency rate. This is the row number 2 who is talking about the transmitted hop rate, and row number 3 come here. So, who is talking about the received FFH MFSK frequency response, where you see at each and every time duration. So, this is the time axis, and what exactly the frequency you are receiving over the time axis is the diagram about. In the first case, you will be receiving F1 okay, plus the FFSK, because that is the modulation, total modulation frequency that you will be receiving, plus some del f changes you are getting. That del f is actually because of the frequency of because of the timing, there is some mismanagement and some mismatch over the frequency also between, and that is a constant del f that is going on for all kind of the for over all the symbols and for all the kind of the frequency for the transmission. And we understand that the receiver frequency synthesizer is not matching with the timing information of the transmitted one, and hence that frequency, that timing gap or mismatch is mentioned here as EPSA. And if that is there, so the whole received signals will have some shift. And mixer output, mixer difference frequency output, if I now try to see, you will be actually obviously getting the output for this zone, this is the left side of this dotted line, and that will be your FIF plus your del f plus your some amount of the FSK. Here actually FFSK will be, in this typical case, this FFSK is equal to 1. And so, this is the way the mixer difference output will be there, and we are really interested actually the output of the detector. And when the signal present sequence is there, detector has got only this much overlapping area to detect, and hence the detector output will be looking like high after the EPSA time interval and of the received sequence, and it will hold good actually uniformly like this. Here is the understanding of the, here we end with the understanding of how this acquisition happens in an FFH as well as SFH MFSK signal, MFSK signals and the systems. And with this in the next module we will continue with some detailed derivatives of this FFH MFSK system to understand what exactly how the acquisition process is going on, and what exactly is the acquisition time for acquisition time required for this active search mechanism in this FFH MFSK systems.